People in the living room. Yo, what's up?
Hello, hello, everyone.
Hello.
What's up, Julian?
Hi.
Whew.
Nick, quick question.
Yo,
So I wasn't here last session. I couldn't make it, unfortunately. Is there a class recording that I could watch back just to catch myself up?
yes, there is. First of all, we have the filled in worksheet from last class posted in the Discord. Are you on the Discord?
No, I'm not.
Okay,
I'll join
I'll
her.
send the Discord link at some point. But we also have a recording. Sarah, you sent the link to the playlist, right? YouTube playlist.
Yeah, I'll go ahead and share that in the chat right now. And
Okay.
then we'll put that in the Discord as well. So that way, at any future point, you guys can either check our solutions or check the recording.
Yeah. Uh, all right, so there's the YouTube playlist link that all the
Uh,
recordings are gonna be posted on. And then here is the Discord link where we're gonna be posting all the worksheets and hosting office hours every day.
Sounds good. Okay, thank you.
Yep. Okay. Well, hello everyone. Welcome back. I hope you're having a wonderful Wednesday. Um, we are going to continue off from where we left off last section. Um, with linear math. We're going to get into systems of equations and graphing linear equations, graphing inequalities. Um, and then we're going to get into some rational stuff, sort of thinking in terms of rational numbers, some of the foundations of that. That's where I'm going to switch it over to Rishi. Um, Rishi, did you have something you wanted to say to start the session?
Yeah, yeah. So, I mean, main thing was, well, I guess I'll say it maybe in a little bit. I mean, as sorry, we were talking about this beforehand. Let's see. Yeah, I mean, I'll go ahead and say it in a bit. I mean, you just go ahead and start
Okay,
off with.
okay. Yeah, no problem. All right. Let's get started. Let's not delay any further. Um, Let me hop on over to my iPad and get screen sharing. Wonderful. Oh, awesome. You can see me. Okay. Yeah, too much, Nick. I'm even sick of it. And it's my face. Okay. So we're gonna start off by talking about systems of equations. Uh, Now I hope by the end of this, and I hope you have a good sense of systems of equations, at least after we talk about this, because you're never going to be able to get rid of them. They're going to be one of the most pervasive things you cover uh, all throughout math. Um, and they're pretty important because as it turns out, solving linked systems with multiple variables is very, very relevant to all sorts of stuff in any engineering you do. So yeah, uh, let's get into it. So, a system of equation, or at least a system of linear equations, is anytime we have multiple equations of variables such as x, y, with just coefficients that are all added up together and equal to some constant. Now, if you have multiple systems of equations, then solving a system of equations is akin to finding the values of the variables x and y that satisfy both equations. So that's our goal when we see stuff like this. And there's a couple ways to interpret this. First of all, since you can represent any linear equation as a line, such as y equals minus x, y equals x plus 6, stuff like that, then finding the solution to a system of two equations is finding the coordinate that falls on both lines, finding the pair of x and y that satisfies both equations. To actually find this value, we usually don't graph and find the intersection. It's actually much better to do one of these other two methods, which are elimination, where we multiply an entire equation by some constant and then subtract it from another equation, essentially trying to, here you can see an example of us canceling out the x. So we're just left with an expression that has y and a constant, where we solve for that and then plug this y back in to solve for x. That's a very common way to do it, manipulating the whole equations. Another way to do it, which I think we may have even done in an example, is substitution, where we isolate in one of the equations an expression in terms of one variable, such as, oh, these are two different equations. For example, if we have this equation here, 3x minus 7y equals minus 14, we could write that as 3x equals minus or equals 7y minus 14, and ultimately get some expression that looks like x equals 7/3 y minus 14 over 3, right? We have some expression for x in terms of y that we could then take and plug in to the other equation. Then we'll just have an expression with just y and we can solve like that. So those are typically the two main ways we solve these kinds of systems. And we'll do some examples like that, but hopefully you should be familiar with both of those methods after some practice. Okay. So slightly switching gears, but it is all relevant to each other, is graphing inequalities. So at this point, we know how to graph lines that are in this form or even other forms. But we were talking about inequalities yesterday, and graphing an inequality is sort of weird. What we end up doing is we end up graphing a line, and then because what an inequality is saying, for example, this inequality right here is saying it's referring to all the values of y that are greater than or equal to 2x minus 3. So it's no longer referring to just one line, it's all the values of y that are greater than that line. And so what that inequality is referring to is all of this space up here that is above that line or greater than that line. Now, the difference between greater than or equal to is whether or not the line itself is considered as a valid solution to our system. So if you have a greater than or equal to, that means that a point on the line is considered a valid solution. If you have just the greater than or no greater than or equal to, then a point on this line is not considered as a solution. And when we graph it, we typically do that, we indicate that by making the line dotted or dashed if it is just greater than or less than and not equal to, and we make it a solid line if it's greater than equal to. So if you see a graph on the MPE, for example, and it's an inequality and the line is shaded versus dotted, then you will know what that's referring to. And yeah, okay. So then you may end up with a system of inequalities. So for example, we have a line here, this orange line that I'm kind of shading with the same color to make it the least amount visible as possible. This line here. Say we have an inequality that's referring to all of the values less than that line are valid solutions to that equation. But say we have a different inequality as well, marked by this green line, and the solutions to that equation are once again all of the values less than or equal to that line. Now if we take both of these lines, or both of these inequalities, combine them into a system, we can start to define certain regions of the graph that may satisfy one line, but not the other, or satisfy one inequality, but not the other. So for example, I mean, it's all drawn. I don't need to redraw it. So you see this line here, this region D. And if we call this orange line, line 1, we call this green line, line 2, region D satisfies line 1. It is less than or equal to line 1, but does not satisfy line 2. Right? It's not less than that line 2, but it is less than that line 1. The same kind of thing happens with B, where B satisfies 2, but does not satisfy 1. And when we talk about a solution to a system of inequalities, remember, for a system of equations, a solution is finding the intersection point of two lines. For a system of inequalities, it's finding the region of the graph, which in this case is going to be region C, that satisfies both. So inequality 1, that orange region, inequality 2, that green region, the overlap of that region is the solution to that system. Okay. Hopefully that made sense. We'll do kind of an example of that in a sec. But okay. In the interest of moving on to examples, quickly, we'll cover this last topic real quick, which is transformations. And we're getting a little bit ahead into what we're going to talk about in the graph section here. But what we do to an equation of a line, or any graph for that matter, directly is reflected by what the graph ends up looking like. And if we sort of study how the equation, how we can modify the equation to change the graph, we can sort of predict what's going to happen to the graph. And so these are very, very general forms of equations where we just have some arbitrary function here that we're graphing, f of x. And by doing stuff to both the inside, the input here, and to the outside, we can change the look of the graph. So if we have something in this format here, we can start by saying, well, all right, let's look at this piece by piece. What is h? H is some value that's being added to x, which is our horizontal input, right? So that means whenever we choose a value on our graph x, before anything else happens, some number is being added to that x, and then it's being plugged into the function, right? Now, the impact this ends up having is shifting your entire graph left or right, depending on the sign, by h. So the reason for this is if you plug in x equals 1, you're going to graph something at x equals 1, right? X equals 1. But before you even calculate the function, you add 3 to it, you're going to get the value that you would have gotten at, for example, x equals 4. Now that's going to be at x equals 1 because you've added a 3 to your input, right? So you're going to be plotting it at x equals 1, but you're getting the value that would have been at x equals 4. And this is going to happen all the way down the line. That's what results in a sort of horizontal shift. And you see that adding something to x is going to shift it left, and subtracting something from x is going to shift it to the right, as we see here. Okay. We can also vertically shift stuff. Now this is a lot simpler. This is similar to what we did with linear equations, where if you just add a constant to a graph, it's essentially going to shift everything up or down by that constant, right? So this k at the very end is the vertical shift. Then we have this factor a that deals with how much it gets stretched and compressed vertically. It just does so by any output value it calculates gets multiplied by some factor. So if that factor is greater than 1, it's going to stretch out your output graph. If it's less than 1, it's going to shrink it down, right? So for for a positive but less than 1, it's going to be squished. For a greater than 1, it's going to be stretched. And for a less than 0, so negative, it's going to be flipped upside down. And that just is because any value that was positive is now negative. Any value that was negative is now positive. So it flips the whole thing. And then the last thing we'll typically see is a horizontal stretch. This is the number that actually gets multiplied by x here when we're doing the calculation. And so similar to how adding a number to x shifts everything over, multiplying the input by some scale factor is going to scale everything horizontally, right? If we're compressing it, the input like this, we're going to be compressing the whole function into. So similar rules for a small positive stretch factor, it's going to squish. For a large positive stretch factor, it's going to stretch. And for a negative stretch factor, it's going to invert on itself. Yeah, or is flipped across the y-axis is a better way to say that. Okay. And if we are trying to picture how our transformations are going to look on the actual, if we plug it into our graphing calculator, what happens? We can look at our equation and we can start with we could plot our standard f of x and then do these steps one by one and ultimately arrive at what our transformed equation should look like. So this is typically the order. You usually do the compression or the stretch factor vertically first, then you do the shift, then you horizontally shift, horizontally shift, and then you do the horizontal stretch or compression. Okay, cool. This was a tricky topic for me. That's why I've kind of gone more into it. I don't know how you guys were taught this stuff in high school, but I definitely was not satisfied with the explanation of any of this stuff when I took it. So hopefully that makes a little more sense. And if that makes sense, then we will go ahead and move into some examples with inequalities and stuff. Feel free to raise your hand or send any messages in the chat if you have questions. But otherwise, let's talk inequalities. So, first question is about vacationing and money managing. Very relevant. So if you have budgeted $480 to spend on food for a trip, and you know that each day at least $25 is going to be spent for food. For the purposes of this problem, by the way, we'll be assuming that whatever number you choose to spend on food, you'll spend the same amount on every day. So that'll just prevent any kind of weird fluctuation. Okay. We want the vacation to last at least 10 days. We're burnt out from work. And we want to create a system of equations where X is the number of days on the vacation and Y is the amount of money. Okay. So what are we actually trying to do here? Well, similar to a problem we solved yesterday, we kind of want to graph to get an idea of how much money are we going to have on any given day, right? And what is the least amount of money? Like, what is the most money we could save and still satisfy everything? And what is the most money we could spend? So, okay. Well, based on a description of the problem, what is our best strategy if we just want to save as much money as possible from this $480? And feel free to type in chat. What's the minimum amount of money that we could still get away with on this trip? I like what I see. Yeah. Yeah, so the most important thing, we're spending the least amount of money per day, right? We want to know the least amount of money we could spend on this trip. We'll make it 25. So, okay. If we have Y as our money remaining and X as our number of vacation days, what is that graph going to look like? It's probably going to look like the slope. We lose $25 per day, so that's a minus 25. How much money do we start with on day 0? Well, it tells us 480, right? And, if we're probably gonna have to do this by increments of like 100. So if we have like 100, 200, all the way up to 500. Then the first day we're gonna be up here. And then we're gonna go down $25 per day, which will have days just be one square like this. So that's going to be something like that kind of slope. Something like that, like half a square per day. And this is our upper limit of Y equals minus 25x plus 480. Now, what is the most amount of money we could spend and still have a good vacation? 475. That's not the most money we could spend. What's the most money we literally could spend? Yeah, 480, right? Literally leaving us with $0 left over at the end. So basically, a line that looks something like, oh no, it's gonna try and snap it to it. No. It's because it's too close to 45 degrees. Okay, that's good. Then it looks like that, right? Now, okay. So we know, what have we gained from this? Well, effectively, the amount of money that we'll have available to us on any given day falls somewhere in this region. Oh, my iPad's lagging. Uh-oh. Okay, there we go. This is the region of potential amount of money that we can have, right? Now, this lower equation here is plotted by minus, and this is going to be, we can calculate our slope. We spend $480 in 10 days. So our slope is going to be 480 over 10, which is minus 48x plus 480. So in the end, we want to describe this system. We know that y has to be less than or equal to minus 25x plus 480. Because that's the least we could possibly, yeah, that's the least we could possibly spend. We also know that y has to be greater than minus 48x plus 480. And here we've created a system of inequalities that describe exactly how much money we'd have based on sort of the range we're given. Does that make sense? Sort of what we did there? Plotting out that region based on what we're given in the problem. Feel free to drop a reaction. Maybe what's a good reaction? Thumbs up if it's good, and then open mouth emoji if it didn't make too much sense. Okay, wonderful. Wonderful. I love to see it. Okay. I'm gonna do 3.4 right now. And then after that, I'm actually gonna want to have you guys try your hand at 3.3 because I think that would be an interesting one to try. Sort of get a pulse check on where we're at. So 3.4, we're gonna try and identify and solve a system of equations. So as we talked about before, we know how to do that. Defined by this line here. And a second line that's perpendicular to the first, whose x-intercept is 6. Okay. So first of all, we're solving a system of two equations, right? One of them we're just given, and the second one is the equation of a line perpendicular to this first one with this x-intercept. So, okay, we can't solve the system of equations if we don't have the second equation, right? So let's start by finding the equation of this second line. So I'm first going to put this equation here into a form that is maybe a little easier to work with and get information from. I'm going to do that by isolating y over here and then dividing both sides by 4 to get this equation, which we may recognize as what form is this equation in? If we remember the terminology. Y equals mx plus b, slope intercept. Love to see it. Yeah. Okay. So this is our first equation. Now we know the second equation is perpendicular to the first one. Do you remember what we said about a perpendicular slope. Remember, we had some difficulty nailing down the exact definition yesterday, but perfect. That is exactly what it's going to be. To find the perpendicular slope, and I don't know if you've seen this symbol before, this upside down T, but that is referring to perpendicular. A perpendicular slope is the negative reciprocal of the original slope. So where our original slope here is indicated by -3/4, the perpendicular slope is going to equal +4/3. Okay? So we have that slope. Now we know that the x-intercept is 6. So let's go for second equation. We have y equals 4/3 x plus b, right? And it's not the y-intercept is 6, it's the x-intercept. And the way we can see this is the x-intercept is where y is 0, right? It's the place where it crosses the x-axis, so y has to be 0. So knowing this, we can plug in 0 for y, and we know that the x-intercept, or the x-coordinate where y is 0, is 6. So we can plug in like that. Now we have something we can easily solve. I can subtract this 6 times 4/3 over here. Now this is evaluating out to -24/3, which we can simplify down to 8. So this is -8 equals b. So now we have our two equations here. Y equals -3/4 minus 1. Oh, -3/4 x minus 1. And y equals 4/3 x minus 8. Now, we actually are set up very nicely here for a substitution. We have two things that are both in terms of y. So if we set them equal to each other, we can find the x-coordinate that must result in these two being equal. So set equal to each other. So -3/4 x minus 1 equals 4/3 x minus 8. Like so. Now I'm going to add 8 to both sides. And I'm going to add 3/4 x to both sides, which is going to give us a 7 over here. And it's going to give us whatever 4/3 plus 3/4 x over here. I'm running out of space, so I may, I'm just gonna add a new page so it doesn't get too crowded. Okay. 7 equals now, if we try and find a common denominator, we can go ahead and multiply 4/3 by 4 on the top and bottom to get 16/12. And we can multiply 3/4 by 3 on the top and bottom to get 9/12. So 7 is going to equal 25/12 x. And then dividing both sides by 25/12, we get 7 times 12/25. And ultimately, this is gonna go ahead and give us 84 over 25 as our value for x. Now we're not done. We've only found the x coordinate where these two lines intersect. Now we can pick either of the two equations and plug this in and get the y value. So y equals, here we'll use this first equation, minus 3/4 x minus 1. We can plug in minus 3/4 times 84 over 25, a disgusting looking fraction. And ultimately, we are going to get, is this even going to simplify nicely? I might have to grab my calculator and switch to decimal mode because it does not look like this is going to simplify very nicely. Does anyone have their calculator on them? Want to evaluate this real quick?
Well, you should get, let's see, negative 252 over 100, and so minus 1. From that, you're going to get negative 352 over 100.
Okay. Minus 352 over 100, or minus 3.52.
Yeah.
Yeah. Okay. Cool. And this is some 3-point number. I don't even know. We can multiply this by 4. I don't know. It's we got our answer. We got our answer. We can put them with common denominators or just leave it at that. In the interest of time, we'll leave it at that. But we found the x and y coordinates that give us the solution, and we're good to go. Okay. How's everyone feeling about that problem? Feeling all right? Feeling good? Obviously the fractions were weird, but if the steps we took made sense, then that's great. Okay, cool. So Rishi, what do you say? Do we have the time to head into breakout rooms and work on this 3.3, or should we just go ahead and work through it and be done with linear?
What I'll say is, we'll pass it on to you guys actually. So we'll ask you that question. Let's use the let's see a thumbs up if you want to see or spend more time on 3.3, and the open mouth emoji if you want to spend more time on fractional rational equations. So anything with like a lot of division signs in it. That would be
Yeah.
what I'd be covering next. So yeah, let's see a reaction from, I saw a couple of them, but thumbs up if you want to see more of this. Open mouth emoji if you want to see new stuff more.
All right. Oh, look at that. All
Okay,
right.
well there's our answer.
Sounds
There's
good.
our answer.
Sounds good. All right. Well, I will pass it over to Rishi. I'm sorry, Julian. I will say I do have like a nicely drawn out or nicely written out explanation of this on the solutions that I'll post after this. But I highly encourage you guys to look at some of those learning modules and mess around on Desmos, specifically on this graphing fraction stuff, because it can get pretty tricky. And I'm if I have a good intuition about what the test is gonna ask you about, I just swear they're gonna ask about what is the graph of this function gonna look like based on the equation. And so I think it would be helpful to review it. But that's linear. That's one of our 6 sections done. So round of applause for us before we move on into the second one. Woo!
Nice, nice.
Okay.
Yeah, and then that kind of, leads into the point I was thinking about making earlier, which is just generally speaking, guys, the one thing I want to say to all of you here, or even those of you who are watching the recording, because I know, it's the summertime, maybe you're like you want to spend your 2:30 to 4 o'clock at the park playing basketball or whatever it is, and you're going to take a look at this later tonight. One thing I want to say is that this test that you guys are preparing for, the easiest thing that you can do for yourself is going to be to immerse yourself in as many problems as possible. So attending this session is a great first step. Exploring the website, the MPE website is always good. Attending our office hours, anything like that. So keep on doing what you're doing, guys. You're doing great. And we are going to jump into rational expressions. So based on what you guys were saying, it seems like rational expressions for most people, this isn't like a one size fits all, but rational expressions, you guys are feeling so on it, right? Maybe a little bit less confident than you are on linear equations, which makes sense. Fractions are a little bit more complicated. And so we're going to spend a little bit more time today on the RATL section. So that's what they abbreviate, rational something, and RATL for some reason. But yeah, let's get into it. The worksheet for this section is already posted in the worksheets channel of the Discord. If anyone needs the Discord link, it's posted by Nick in this Zoom chat already. In the chat towards the beginning of the section, and so go ahead and check the worksheets channel for all the problems I'm going to be looking over today. And get out your paper and pencil. Let's see. Okay, so I will share my screen. All right. So irrational numbers and equations. That's what we're going to be talking about. Just as a kind of brief overview, because I know, I just want to be completely transparent about what we're going to be doing today. I just want to quickly say, first thing we're going to do, which is the first module, is going to be percents and proportions. So that's just basically, using fractions as a tool. So proportions of anything you might see in your daily life. This is going to be really useful for chemistry, and physics even. Second thing we're going to be talking about our second module is going to be rational expressions. So this is going to be a pretty long section actually, but we're going to get into a whole series of different expressions you might see that all have fractions in them. And then all the way down here, we're going to have inequalities and functions. So similar to what Nick was talking about, but a little bit more dealing with when we have fractions in those inequalities and graphs. So hopefully that all looks, completely interesting and hopefully not completely new to you guys. And just as a reminder, guys, if you have any, questions about like, oh, I haven't really seen this before, what's going on? Please feel free to stick around at the end of the section for my office hours. They're going to be directly after the section every day for 4 to 5 p.m. So just stay after, and if you have any doubts, just ask me then. Cool. Enough talk. Let's get into it. Okay. So first section, as I was saying, we're going to be using proportions as a tool. Okay. I just want to draw attention to this example down here, right? For example, if we have 8 workers can build a house in 4 days, then how many workers does it take to build a house in 1 day? Right, so we have 2 pieces of information. Fractions are a great way to relate 2 things because you can have the denominator be one thing and the numerator be another thing. So what we're doing here is we're just going to have the numerator be house and the denominator be days. So we can break down this information into houses per day based on what the workload is of a worker. All right, so 8 workers for 1 house in 4 days. Then we would need 4 times 8 workers to get 4 houses in 4 days. So we can use a quick little multiplication times 4 in order to work out 4 times the rate to get the answer of 36 workers will build 1 house in 1 day. So just a quick little example. It's already on your page, so don't worry about writing it down. In these worksheets, again, the solutions will be posted in the Discord. But just a way to visualize numerically how we can talk about rates. One thing that's going to come up in a lot is chemistry, as I kind of mentioned. So we're going to do this quick little example, number 1.2. That one is a little bit more of a,
Oh yeah, I gotta link the worksheet. I'll do that.
oh, yeah. So I sent it in the Discord, but yeah, that'd be great. Thank you. Sure. We're going to start with a little bit more of a, everyday example, talking about discounts. Okay, yesterday was Prime Day for those of you who have Amazon Prime, so you might have been doing something similar to this in your own everyday life. Okay, Prime Day, let's say they had an item that costs $100. Okay, so they're talking about some sort of pretty fancy gaming headset. I don't know, $100 cost. It's discounted 25%. Take that discounted price and increase it again. Now, I don't know why they'd increase it again. That seems like a pretty bad deal, but let's just see what would happen. So, problem one here. Oh, let me just, problem one. We are going to use these fractions to our advantage. $100. And then what we're going to do is multiply by whatever our ratio is. So here we don't really need to use a fraction because our only actual unit is dollars. So in a problem where you have multiple units, such as Rattle 1.4, we have multiple units. But for this one, since there's only one unit, there's no fractions necessary. We're just going to use a multiplier of 0.75, right? So if it's discounted by 25%, that means you're paying 0.75 of the total cost, which is going to get you $75. Then it says increase that price by 25%. So we're going to take that $75 and then an increase of 25%. So full price is 100%. If we add 25%, we're going to multiply by 1.25, which will get us a grand total of $93.75. So it turns out it actually was a good deal. So decreasing the price by 25% and then increasing it again is a good deal because you have to keep in mind, right? What are we multiplying by? In this first part, we were multiplying by 100. In the second part, we were multiplying by 75. Makes a big difference. Cool. And again, feel free to shout out, if I'm looking down at my iPad, I'm writing out the solution, feel free to unmute yourself or, type in the chat. Nick will let me know if there's a question. So please feel free to raise your hand or interrupt at any point. Real quick, part two of this problem. Part two, if we have an item, we take 50% off of that item that costs 100% or $100. So those gaming headphones or whatever it is. And then further reduce it by 50%. Do you get that item free of cost? Seems like a pretty good deal. Let's say somehow, on Prime Day, they have a 50% off sale, but then those headphones are already 50% off. I mean, what's going to happen, right? The way we can kind of display that here would just be $100 times 0.5 because it's 50% off. That's going to equal $50. And then we take that reduced cost of $50 and we multiply it again by 0.5 because it's 50% off to get $25. So it's not free, unfortunately, right? You can't stack these things, but $25 is a lot less than 100, so that's still be a pretty good deal. Again, the key point there, guys, is what are we looking at, right? In the first part, we were looking at $100. In the second part, we were looking at $50. So don't go back to the first number. Make sure you take your answer from the first step and then carry it through to the second step. And so I like to just box my answers when I'm done. It's going to be pretty useful in a lot of your math classes, chemistry classes, physics classes, engineering classes, pretty much all of your classes, actually. And Nick can verify, guys. He graduated from UCSD with a excellent GPA, I'm sure. So he can verify that boxing your answers is, a life hack. All right, any questions with problem 1.2? Well, it's true, you did graduate, so yeah, you must have done something right. All right. Cool. Well, pretty straightforward problem. We're going to jump a little bit more into using the actual ratios in problem 1.4. So we're going to be talking about liters and alcohol solution. So this is a very common type of problem you might have in Chem 6A. And these are exactly the type of classes you'll be hopefully taking some point during your freshman year, right? Which will be assisted by the fact that you guys do really well on your MPE. So make sure you guys nail that MPE and you can get into chemistry and then you can get into a bunch of other fun classes, right? Anyways, jumping into it, problem like this, what I like to do, since there's so many things going on, we have, so, I'm reading this problem, I'm seeing like liters and alcohol and percentages. It's it's all very confusing. So what I'm going to do to simplify all that information is create a table. So I'm going to create one row for the 70% solution, one row for the 40% solution, and one row for the 50% solution. Those are just the three solutions they talked about in the problem. So what I'm going to do is talk about the liters of solution, the proportion of alcohol in each of those solutions, and the total liters of alcohol. As a quick little table. This will just help me visualize the information, right? So that's definitely a technique I recommend is when you're given a bunch of words in a problem, whether it be in math or another class, if there's numbers especially, it's best to kind of collect and gather that in whatever way works best for you. Maybe you prefer systems of equations, maybe you prefer drawing a graph, it's up to you. But for me, I'm going to make this table. It's saying how many liters of a 70% alcohol solution, which means that this is a question mark. We don't really know how many liters of 70% solution we have. So I'm just going to write X, right? That's what we're solving for. How many, right? That's a big indicator of that's our answer is X. And then it's saying how many liters must be added to 50 liters of 40% alcohol solution. So this is going to be 50 liters to produce a 50% alcohol solution. And so if our 50% is our total, like that's what we're going to have in the end, is a 50% alcohol solution, the number of liters better be equal to whatever our X is plus 50, right? Since we're going to add these first two rows together to get our third row. Then we can write our proportion of alcohol. So that's just going to be 0.70, 0.40, and 0.50. The proportion of alcohol is just the percentage of alcohol. And then the kind of tricky part is the total liters of alcohol. So the total liters of alcohol just means how much alcohol is there within each of these solutions. And so it's just the proportion multiplied by the total liters. So solution, if you guys don't know, is just something where you mix two things together. So if it's 70% alcohol, that means it's 70% of, alcohol, and then 30% something else. So the total liters for this are going to be 0.7 times X. And then for our second row, total liters of alcohol, when we have 40% alcohol for 50 liters, it's just going to be 0.40 times 50. And then last but not least, for our last row, we're going to multiply our proportion times our total liters of solution. Any questions so far? All right. Continuing on, we got to actually, find what X is. So the way I'm going to do that is going to be looking at this problem, we have a 70%, we have 40%, and they must be added, okay? Which means all I'm going to do is add together. I'm going to add these two together. .70x plus 0.40 times 50. And that's going to be equal to our 50% solution. So this is going to be our equals on the right hand side of this equal sign here. So that's going to be 0.50 times x plus 50. All right, so our two things are being added into one, added to be equal to one thing. So just simplifying this down a little bit, we'll get 0.70x plus, let's see, 0.4 of 50 is going to be 20. That's going to be equal to 0.50x plus 25. If I subtract 0.50 from each side, or sorry, 0.50x from each side, I'll get 0.20x. And if I subtract 20 from each side, I'll get 5 on the right-hand side. So x equals 25 liters. All right, so 0.2 is like 1/5. And so to get rid of that 0.2, I just multiply both sides by 5. And then I box my answer. Any questions? Yeah, I mean, getting into fractions, that's kind of like the base use of fractions. But we're going to continue on talking more and more about longer applications of fractions. So there's a lot of information on this worksheet, guys. I don't want to spend a ton of time just kind of reading off the worksheet. So what I'm going to do is kind of summarize the information on here. But this will be kind of your handbook through what's going to be on the MP, right? So I do recommend you guys go back to this worksheet, review it, read through it, and do any of the problems that we skipped. So, oh, and then Nick, we also should mention the problem sets, right? So
Yeah, so at the end of each worksheet, we have some practice problems that will also have solutions to that we will not be going over in section, but that are generally all encompassing of what we talk about. So on your own time, that would be if you don't feel like going and digging for more practice problems, then there's some good practice problems at the end of each worksheet.
cool. Thank you, Nick. Yeah, so pretty much at the bottom of each of these worksheets, you will see after the very last module, you'll see these problem sets. So those are kind of like what you would consider your homework problems. And we will have the solutions for those also posted with the worksheets. So it's all going to be in one document, nice and easy. I highly recommend you do these if you have some extra time and extra practice, right? But and so I guess the point there being, guys, we recommend for today you guys should look at the linear practice problem set because we finished linear equations today. Okay, so jumping into our second module, dealing with rational expressions. Okay, so first thing I want to point out is the difference between rational numbers and irrational numbers. So the rational numbers, and just to kind of make it simple, rational means fractions, okay? The word comes from ratio, and so ratio is like, 3 to 2, 1 to 2, 7 to 5, whatever it is. So anytime you have a number that could be represented as a ratio, it's rational. However, there are some numbers that are irrational. Pi is irrational because it's a decimal number that doesn't really have a ratio attached to it. And we could also have some other examples with radical signs. So those are like our square roots, I suppose. So that's just the difference between rational numbers and irrational numbers. Just a quick little vocab for you. So if you're someone who likes to, highlight, here I have my highlighter tool. Go ahead and highlight rational, highlight irrational. I like to highlight my vocabulary as I go through. That way, when I'm studying for the MPE, the day before I'm taking it or whatever it is, I can go through my worksheets and quickly recall, okay, these are what all these different words mean, right? Plain and simple, it's just a way to remember. Prime factorizations. Can I get a thumbs up? Have you seen prime factorizations before? And no worries if not. I mean, I'm just trying to kind of gauge here. Okay, so a few of us have seen it. Cool. So essentially, the definition is right here. Prime factorization, it's when we express a number as the product of only prime numbers. So prime numbers, there's a series of numbers that are prime. It means that they can be divided to be like a smaller number, a smaller prime number. So this is kind of like the bare bones way of expressing a number. So 24 is not a prime number because it can be divided by 2, it can be divided by 3, it can be divided by any number of other numbers. So this isn't something that comes up a ton, but it is a good vocab word to know as well. So let me go ahead and highlight that as well. So prime numbers can also be a vocab word, right? Nothing super crazy, just wanted to point that out for you guys. Moving on, multiplying rational expressions and trinomials. So who has seen this method before, the X box or box and X method before? Got you. Okay, cool. So I'll go over it briefly. Seems like most of us have seen that. However, again, if you have any questions about this, please come to my office hours after the section. In a few words, the box and X method or the X box method is a way to find out how we can take a polynomial and write it out in the form of its factors. So we have this ax squared plus bx plus c, where a, b, and c are just going to be some random coefficients like numbers. The way we find the factors for that is using this box in X, where we have a times c, x, b, and y. So we'll have, and I'll just go jump straight into the example just to kind of illustrate it for us. So if we have this 2x squared plus 9x plus 10 polynomial, if we were to compare this to this, what we kind of say is that 2 equals A, and then we could say that 9 equals B, and then we could say that 10 equals C. So using the box in X method, the top here is going to be A times C, which is 20. Then we have our B is at the bottom as 9. And then we have okay, yeah. And then our factors for, it's a little bit small here actually, but that's a real important one. X and Y must multiply together to equal A times C. So pretty much our factors for 20 are going to be two numbers, 4 and 5, which are also, if you note, added together to make 9. So X and Y must add them together to equal 9. So it's kind of like a puzzle, right? So which two numbers can you multiply to equal 20, but you can add them to equal 9, right? 4 plus 5 equals 9. And then 4 times 5 equals 20. Cool. Then what you can do is kind of write out your answer in that form. So using that information, you can rewrite your original polynomial by breaking up that 9 into the 4 and the 5, and then you can break it up further by factoring each of those sections, right? So we have kind of like two halves here. We have this half, we have this half, and we can break that up further and further into like its smallest factors. Cool. Well, I said I'd keep it brief, so we're gonna move right on. Okay, multiplying rational expressions, part 2. So this is going to be talking more about a lot more dividing and when we have larger division signs and problems. So a lot of what we're going to do is dividing by the same thing on the top and the bottom. So anytime we have a bunch of polynomials, what we do is we multiply by equals on the top and the or equivalent polynomials on the top and the bottom. So here we have what's essentially a 1, right? This whole thing is equal to 1. Like we're essentially 1 times whatever we have, except we're using that 1 in a very specific way, right? We are using this x plus 2 times x plus 5 divided by x plus 2 plus x times x plus 5. And on the right side, there's another one in a way that's going to make my life easier, as it says. So first thing I do is I factor whatever polynomials I have. The second thing I do is try to multiply out by a 1 in order to solve the problem. So, this will kind of vary case by case, but the more problems you do, the more it'll become easier to figure out which ones you're going to use. And by 1, I mean which kind of fractional polynomials you're going to use. So multiplying is a little bit easier. All we have to do is multiply the top by itself, or like multiply across the top, and then multiply across the bottom. So x minus 3 times x plus 3 is equal to x squared minus 9. X plus 4 times x plus 7 is equal to x squared plus 11 x plus 28. And if you need help with how to find that out, feel free to raise your hand or anything like that. And then if you want to divide two fractions, you must flip the divisor. So it's the same thing as multiplication, except here, we're dividing two fractions. So that's the same as multiplying the inverse of the second one. All right, so the first guy stays the same, the second fraction there flips. The top becomes the bottom becomes the top. And then from there, you can just continue through and simplify. I know it's a lot of information here, but we're almost done. We just have one more box. Essentially, when we're solving rational expressions, we're just going to solve for x in any other way that we normally would. This is kind of highlighting the fact that we want to first get rid of the fraction. That's the main thing. So here we have some two fractions that are equivalent. Very first step I'm going to do is cross multiply. So cross multiplication is when we multiply we're essentially going to multiply the top of the left side by the bottom of the right side. And we're going to multiply the bottom of the left side times the top of the right side. It's supposed to be like a multiplication sign, but it's kind of hard to kind of hard to see. Hopefully, though, you'll see down here that we're multiplying. And then from there, it becomes a little bit simpler. We can carry through that 7 and then solve for x. Cool. I know that was a ton of information, guys. but it seemed like we were feeling pretty confident on most of it. So I'll stop right here for a second, just pause and ask, are there any questions? Okay, cool. Well, at the very least, I hope you guys are kind of refreshing and getting used to this information. Um, maybe you've seen it before recently, maybe it's been a few years. So review is always, good to get your mind caught up, right? Okay. Real quick, let's look at 2.3. So using that second to last thing I explained, we're just going to go ahead and solve both A and B. So feel free to work on your own and check your answer as I'm working, but get out a piece of paper, try this problem. Essentially, anytime we're dividing two fractions, what I'm going to do is divide the second fraction by, or flip it, sorry, not divide it, but flip it upside down. That's going to make our division sign a multiplication sign. So all I did that first step is I just flipped. And then from there, I can multiply across. So I'm going to multiply the top all in one step, right? So I'm just going to multiply this by everything over here, and I'm going to multiply the bottom by everything over there. Except when I'm looking at this, I can also note that we can simplify this whole thing, right? This and this cancel out because they're equivalent, right? If we have the same thing on the top, the same thing on the bottom, they become a 1. They cancel out. So all we're left with is 4r squared over 4. However, if those two weren't equivalent by chance, then what I would do is just multiply across the top, across the bottom, and we'd get the same answer. So from here, 4r squared over 4 is just going to be r squared. Nothing super crazy, but just using our rules. Moving on. Part B. Same first step. I'm just going to flip the second fraction, flip it upside down, and then make this division sign a multiplication sign. Then I can multiply across. Multiply across, what I mean is everything that's in the numerator, I keep in the numerator of the resultant. Everything in the denominator, I keep in the denominator. Before I even get there, though, I'm going to simplify this a little bit further by canceling out this x on top, this x squared, by this x on the bottom. So one of those x's on the top will cancel with one of the x's on the bottom, which means all I have to keep in mind now is x, this x right here, this x squared plus minus 1, and this x plus 1. So what I'll get is x times x squared minus 1 divided by 1 plus x. Now we can use one of our factoring rules. So what I can do is think about what that x squared minus 1 could be simplified further to be. What are its factors? So anytime we have a squared, a minus a number, that also happens to be a square. So if anytime there's like a x squared minus 9 or an x squared minus 1 or an x squared let's see, minus 16, the factor is just going to be x plus whatever that, if that number is squared, so these are all squares, it's going to be x plus whatever that square root is, the difference of perfect squares. Thank you, Nick. See, I don't know the names for all these things, but it's good to know. It's good to know. It's going to be whatever that square root is of that square. So x plus 3 times x plus, or x minus 3. And that's going to be, x squared minus 1 would be equal to x plus 1, x minus 1, and then x squared minus 16 would be equal to x plus 4, x minus 4. So you'll see the pattern. It's x plus the number times x minus the number. For this example, we're going to have x times x minus 1, x plus 1, divided by 1 plus x, which is equal to x plus 1. So this cancels out. This cancels out with this. The x plus 1s cancel out. We should get x times x minus 1. This is our final answer. You could also simplify that, well, or rewrite it another way as x squared minus x. Both of those would be valid answers. They're just saying simplify this, or at least it's supposed to say simplify this. And so both of those are simplified as far as you can go. All right. So to finish up for today, thank you guys for bearing with us. I want to end off with a word problem. So we're going to create a breakout room. The main thing I want you guys to do, or Nick, do you want to introduce your icebreaker? No. Okay, sure. I'll do it then. Nick had an icebreaker. I liked it. I'm just gonna break you guys up into just two groups to make it a little bit easier, so we have enough time to all talk. I'm going to ask you guys to, or Nick's idea was, I'm going to ask you guys to share one thing you have done this summer, which is like super fun and awesome, or maybe it's not that fun, but it's the funnest thing you can think of. And then think of one thing that you have yet to do this summer. That's hopefully also fun. Maybe your thing is like taking the MPE. I don't know. Maybe you really want to take the math placement exam. I don't know. But I'm gonna assign you guys to breakout rooms right now. And you should go ahead and head back here in 10 minutes. All right. Well, while you guys were away, I wrote up the solution. Just kidding. I already wrote the solution before the section, but here it is in case anyone is curious. So for the first part, Anna and Carlos should make the dinners. Bill and Diane should make the desserts. And then you can see a little bit of the work of how much time it'll take each of those teams to finish their tasks. But hopefully you guys got to get the chance to talk to each other a little bit more. The solutions will be posted. Thank you, Sarah. You're perfectly on top of it. Click on that link if you want to join office hours with me directly after this. Nick, you got anything else?
I'm also hosting my own office hours daily right now. They're scheduled, or they're not even scheduled. I'm just gonna be in the Discord from 1:30 to 2:30 right before the section. If you want to hop in the Discord. Otherwise, if that time doesn't work, I understand that going back to back may be awkward. I put up a poll in the Discord in the announcements channel. If that time doesn't sound good, feel free to vote on what you think an alternative time should be. That's pretty much it for me.
All right. Well, have a good rest of your day, guys, and I'll see you guys in that Discord office hour or my office hour right after this.
Yeah. All right. Peace out, Girl Scouts.
Bye bye.